Good evening, everybody, and welcome to the Luxoft Technology Series. My name is Shai Almog, and I'm a Vice President for Global Marketing at Luxoft. And thank you for joining our first webinar in the Luxoft Technology Series. I hope you can hear and see us okay. So if you just type quickly in the chat window that the audio as well as the video is okay, I would appreciate it if you get some feedback from the audience. Okay, thank you very much. So before we begin, I'd like to take you through some of the logistics. During the session, there will be three moments where you will be able to ask questions to our guests. There are two ways in which you can ask that question. One is through the WebEx client. There is a section on the bottom of the right-hand side of your screen where you can post a question to our panelists and our guests. And those questions will be reviewed by our moderators, and Shai will answer some of them during our session. You can also ask those questions at Twitter. So if you follow Luxoft at Twitter, if you send a message at Luxoft with the hashtag LTS, we will be able to capture your question. So now I'd like to introduce our guest speaker, Mr. Shai Almog, who's the CEO and co-founder of Codename One company, and is also a Java and mobile development expert with 20+ years of experience in that space. Shai will give you all of the details about his background in a minute, but I'd like to thank you for accepting our invitation. Shai, we have a large audience in front of us. We have people joining us from all over the world and several hundreds of guests in our webinar by now. And thank you again for accepting our invitation. And welcome to Luxoft Technology Series, and the stage is yours.
So thanks for that great introduction, and thank you to Luxoft for inviting me to talk to you today. Thanks especially to Evgenia, who worked so hard to make this whole thing happen, but in general to everyone in Luxoft who worked quite a lot on this. Today we'll talk a bit about mobile development, native mobile development, and mostly native mobile development from the perspective of cross-platform. So how do you actually deal with these native devices when you have to build a cross-platform solution like we had to do? And I think this will be useful for you whether you're using cross-platform technologies or whether you're building native mobile applications, regardless, because these ideas transcend everything. So first, let's talk a bit about what we're the flow of the actual presentation in the session today. So I've generally built something relatively generic because of the large audience involved. So as President said earlier, I hope you ask questions and answer questions during the session. You don't have to wait for a specific question slide, just ask them, and I'll get a condensed version of that when we actually get to our answer slide. And these will be strewn throughout the session, although the first portion will be relatively longer because it will also include the introduction portion and the initial session itself. It's divided from the easier stuff, graphics, and then a bit more complex ideas of graphics, to harder things like AOT, JITs, and stuff like that. Everything is still structured to contain valuable information, whether you're an advanced developer, and even valuable information if you're not as advanced as some other developers. It should be applicable to people who aren't deeply familiar with Java, although I will be biased towards Java, and it's mostly structured to people who are familiar with that environment. In the end, we will have a longer question and answer section that will give you time to ask additional questions. And as far as I understand, we should also have videos with additional answers after the whole session is over. I will spend time recording some additional answers, so be sure to check out the LTS site for additional questions. And as we said earlier, feel free to use Twitter or the question and answer section in the WebEx. So let's proceed. I'll give a bit more of an introduction to you. Not too crazy about the photo they chose to use there. It's a bit old. It shows how much weight I've gained in the startup part. Specifically, I started a consulting company about 14 years ago. And with that consulting company, I sort of ran into all sorts of interesting companies. And the most interesting one was Sun Microsystems, who sort of found me when we were working on this Palm Pilot, first mobile platform, Palm Pilot application in C. And I don't like developing applications in C. It's a great language, but not so much for high-level applications. And the tools for Palm Pilot were awful. But Sun is mobile devices back then was before there was nothing, before there was anything. But didn't run on Linux. So I ported that, and Sun practically found me, gave me a call an hour later, and me and my employees, we started working with Sun, and I got to work on the first Docomo Java phone. Then I got to work on all sorts of other cool things, the first wireless toolkit, which was the first development environment for cross-platform, actually for mobile. And all sorts of other customers and things. We worked a lot with all operators and manufacturers and did lots of cool, interesting things. And at some point, I started working with Ken Fishburne, who's my partner at Codename One, on this really cool cross-device solution for mobile. And eventually, we decided it can't go far enough within Sun or within Oracle. And we left to form Codename One, which I'll talk a bit more about soon enough. But I start every presentation with these two slides. Now, the first slide is the motivation slide. It's essential with every presentation, even if you're a developer, if you're the most technical person, often you're not going far enough backwards to see the big picture of everything, of where your career is going and where do you want to be next. And for business people, sometimes they're not familiar with the numbers, but the numbers are pretty clear. Mobile is where everything is. People say mobile first, all sorts of slogans like that. It's the reality. It's literally, if you're not developing for mobile right now, you will be developing within the next couple of years. The question is of how you will be developing for mobile. And that's the second slide. So if the first slide was mobile is great, mobile is excellent, mobile is wonderful, this one says sort of, well, mobile sucks. And it sucks because when we developed for desktop, we sort of reached a point where you could just press play and it just worked. And with mobile, we sort of regressed a bit on that. We have, I need a Windows 8 machine. I can't use an older machine or anything less than that for developing Windows Phone applications. Now, the smart guys among you will say, oh, I can use virtualization. Well, no, Microsoft blocked that. And, see, I'm losing my hair because of that sort of thing. And it's also hurting my back because I have to carry all of these devices. These devices are actually in my backpack on a regular basis because I might need to do a Windows Phone development. On the other hand, I might need to do iPhone development, so I'll need a Mac for that. And yes, I can theoretically virtualize that, but it's problematic and it's illegal in terms of Apple licensing. I also need a tablet, at least one. I have plenty, but one is a minimum. And one of each device. And this is the minimum set of devices that I need in order to just target all of these. And I'm carrying all this amazingly heavy bulk because I need to build a cross-platform solution. But the idea is that this isn't normal. We don't need to carry all of these everywhere. We do need to test on them. There's no escaping that. Testing has always been a problem on desktop and on mobile. But we don't necessarily have to carry them everywhere. And unless you're a poor staff like myself who actually needs to test everything and build everything natively. So how did we actually get there? Well, there's 11,000 Android devices. I didn't know that until I actually had to check it up in Wikipedia because no one really runs into that. So Android device fragmentation is a bit more complex than most people. I have a lot of thoughts on that, and I have a slide on that later on. So I don't think it's what most people think it is, but 11,000 is a whopping number. It's a big number, and it does have implications. Microsoft, again, reason I'm losing my hair, has 4 mobile operating systems, literally 4. Now, when I say this to people, they say, oh, you're including Windows 8. No, I'm including Windows Mobile, which is still being used, still being produced, still devices coming out with essentially Windows CE. Now it's rare, it's mostly industrial devices, but still, it's the Windows Phone 7 still being manufactured, still being sold. Windows Phone 8 is completely incompatible. Both of those are also incompatible. Windows Phone 8, again, broke compatibility just a couple of years after Windows Phone 7 came out. And Windows RT is the tablet version of their operating system. And that is, the fourth operating system. And they also bought Nokia with additional 3 operating systems. It's hell on wheels, essentially. So, okay, we can't ignore Microsoft. So Apple is at least better. Well, yeah, Apple was great when it had one device, the iPhone, and then it had 2 devices, but that was just doubling, and then it had 3, and then it had 4, and now it's starting to get a bit crowded. And the thing is, when Apple adds a device, it's like adding another 1,000 Android devices. It's got a lot of implications, and Apple wasn't as prepared to the changes that they themselves introduce when compared to how Google was prepared. And I'm not saying that Google was prepared, I'm just saying that Apple wasn't. And it's noticeable. And I won't even talk about BlackBerry. It's painful. Everyone knows it's painful. I think BlackBerry knows it most of all. But generally, the problem is that every company picks a different technology. They don't necessarily do it by choice. There's history. Microsoft came with .NET. Google didn't really have much of a choice other than version of Java. And Apple went with Objective-C mostly because it did that in the 80s when people thought Objective-C was the future. And it's literally inheritance from from Next, and it's based on inspiration from Smalltalk. So anyway, but to me the bottom line is that the vendors aren't necessarily on our side as developers. The vendor's interest is that we will develop their specific operating system, not necessarily the other way around. Our interest as developers is to get as many users as possible and make as much money as possible potentially. So these interests somehow collide at that point because we want to be on as many devices as possible for the least amount of cost. Because the cost isn't just the cost of porting, the cost is the cost of maintenance, of issue tracking, and of bugs in general. Because one thing I've found is that bugs are remarkably portable. And when you do the application several times, you create the same bug over and over again. But if you use one code, you'll fix those all the way through. So that's important, and that's a huge benefit for us. So why did we quit Oracle, that whole cushy job and those great Java 1 all-nighters and everything? Well, we felt that we needed to do this thing. And what we created is effectively an API that allows you to write once for all devices and allows you to build a native application. And this talk will focus about the issues we ran into when we developed this huge API with the environment. Now, and just briefly, Codename 1 allows you to install a NetBeans or Eclipse plugin and essentially build a native application using the cloud. We have Macs in the cloud, we have Windows machines in the cloud, and the jar is sent automatically. The compiled code, it's translated natively, and you get a native application directly to your device. And in order to make it that sort of feel, that sort of Visual Basic like feel, you press play and it sort of works. So much went into. And this presentation is about what we went through in order to give you that sort of experience. So I'm going to start with, obviously 90 minutes isn't that much to explain the full scale, but I'll give you a tip of the iceberg in those regards. And the first is resolutions. Dealing with different resolutions sounds like a huge problem, especially iOS developers make a big deal out of that. Android devices have so many resolutions. And you've got this sort of graph that I actually picked from a website that deals with device fragmentation, and they use it to sort of illustrate in pictures how device fragmentation is hurting Android developers. I don't agree with that. I actually don't think this is fragmentation. I think this is variety, not fragmentation. And we know how to deal with variety. We just build everything to support that variety. But It does illustrate the scale of how many devices we need to support and the sort of variety that we need to attack. To read this graph, you can see that the blue lines are actually, the darker blue lines mean that more devices are targeting that particular resolution. And you can see they cluster around a specific area, but they slowly grow out. If you see it in an animation, you see the blue sort of going further and further upwards. And the thing is that devices don't get bigger. They maintain the same size. Sometimes they will grow, actually, in Android they do grow to some degree. But they grow more in the sense of DPI or PPI. And that is really the interesting portion in what I'm talking about. When we look at these three devices in front of us, an iPhone 5, an iPad mini, and MacBook Air, all of which I have right now. They have resolutions that aren't very different, but the screens are remarkably different. The iPhone has twice the number of pixels than an iPad mini in terms of density in the same surface area. And that means that in an inch, they include double the amount of pixels. And if I take a picture that looks decent on an iPad mini, it would look half the size when I show it on the iPhone. And why is that interesting? Well, that's more interesting than resolution for many use cases. Because when we want to size something so it will be as big as our finger, so it will be touchable, we need to take that into consideration. And these arguments become more complex when we target additional devices like televisions. For instance, an HDTV, this is something that often comes to people as a surprise initially because they don't really, never really thought about it. But an HDTV has a much lower resolution than all of these devices, around 20. And the reason it has such a low resolution, so for instance, 20, and in comparison, the iPhone has 326. So when I'm saying it has such a low DPI in a television, it doesn't really matter to us because we're sitting 6 feet away from the television. But the iPhone we're holding practically to our eye, and we don't need to touch the television on the other hand. So obviously things change in that regard. So this is a very complex dynamic essentially. And we need to think in terms of how we want to build things for that particular resolution. And that's important because we want to adapt the user interface, not just scale it. So we're seeing here two devices. One of them is an iPhone 3GS, and another one is an iPad mini. And they have the same DPI, essentially, plus minus, pretty close. And you'll notice things are sized. These are actual sizes in pixels, actual, not scaled or anything. And you'll notice that they're pretty much sized the same. So the finger would fit just right, regardless. This is one of our coding on demos, by the way. You can try it actually live and see that it works that way. And the thing is, when we run that demo on the iPad, we want it to behave like an iPad. We don't want things to grow because there's more pixels available than the iPhone 3GS. An iPhone 3GS is 320 pixels, about 480 pixels, where the iPad is 768 by 1024. So we don't necessarily want to take all these pixels just by the scaling everything. We want to use these additional pixels in a constructive way. Otherwise, we just have a large phone, not a tablet. It would be like taking a phone application, putting it on your desktop. And the other way around doesn't work either. You can't just take a desktop application and stick it on a tablet. It doesn't work. So how do we solve it? How do we get that sort of interface to match tablets, to match phones that will work in a reasonable way when we switch between the two, and that would still scale well in case we have a Retina device or a high resolution device? Well, each one of the vendors that we're talking about had a solution. So I'm going to go over Apple's solution and over Google's solution, and those will give us the hints on how to write something that allows us to transcend platforms and write a portable solution. So Apple created a solution that matches their specific problem. They initially came out with an iPhone. So the iPhone had a 320 by 480 resolution. And that's very important because they kept that resolution. So when they came out with the iPhone 4, which had double that, they exactly doubled the pixels. So you got 640 by 960 pixels, exactly double. They called it Retina because it's the same a resolution that's supposedly indistinguishable between Retina. Okay, we can debate the marketing terms there, but still great marketing name. And in Retina, because the nice thing about it is that it's exactly double. So if you have an image, like you see the image to your right, we got the standard input text version. So we can load it using, and what you see here is a JavaScript code that essentially creates an image instance. This is sort of like in Java factory method. And you'll notice it's relatively simple, just create an image instance with a name. But if you have another image that has the Retina version, which is marked as 2x, and you're running on a Retina device, it will give you that Retina image. And that's pretty cool because you just work with images and then you make sure to have the high resolution image and it just works. Actually, it works so well that you can't really circumvent it. And when iOS 5.1 was around and we had the iPad 3 came out, there was a bug with the device, and we needed to load the low resolution image in order to do some things with it. And we couldn't. It was a nightmare trying to circumvent this and just opening a file and loading an image without going through this process. So, so when working around bugs, this is really painful to some degree, and that's sort of also a symptom of Apple. Apple sort of tries to simplify things and unify them, and if you try to do things a bit differently, sometimes you get bitten. They also include the ability to design for iPads and iPhones, and essentially for them, it's really simple. There's iPad, there's iPhone, and there's iPhone 5 also, which changed some things, but generally it's relatively simple. They have the same resolution. And when you build your UI, most Apple developers create one layout for iPhone, another layout for iPad, and generally load the right one based on the device. And this is pretty easy to do, and they just rely on that, and that's it. Not much of a rocket science in terms of portability there. Sometimes you can create literally different applications, although you don't technically need to. You can bundle both of them in a single universal application. The main reason that they're doing two separate applications is the monetization thing, where they can charge more for the app. So, and they have one last thing, which is points. So you remember the 320 by 480 resolution thing. Well, the reason they have that resolution, the reason it's important with iOS is that when you position elements in iOS, you position them by points, not by pixels, by default at least. And when you position things by points, you're essentially treating the screen, if we're just looking at iPhone, as if it's 320 by 480, the original iPhone 1. And they automatically scale the points. There's a scale factor. They scale them to match the Retina display when you're running on a Retina device. Now, this is important because you essentially don't get the additional pixels as you would expect to get them as pixels. You sort of work with coordinate system that's relatively uniform. And the pixels are expressed by having the higher resolution image. So the higher resolution image will be rendered properly. So you'll get crisper, nicer images. And the fonts will be rendered crisper because they'll be essentially doubled. So you'll ask for a font that's 13 pixels high, and you'll get a font technically that's a point high. And you'll get technically a font that's 26 pixels high when running on a Retina device. But to you, it will seem like exactly the same code. And that's really nice, and that's a simplification that Apple can do because they have a very well-defined set of devices to begin with. Obviously, that's not necessarily the case for other devices. So Google, on the other hand, have a very, very different environment. they sort of allow anything to exist within their environment. And because of that, they support a really elaborate directory structure that's also changing with additional versions. So they didn't have certain DPIs when they came out, and they had to add them as device densities became greater and greater. And they've constantly added and responded to that. So this directory structure allows an Android developer to essentially create images in different directories. And when you're running on a higher density device, the right image arrives based on the directory where you placed it, or at least the closest approximation. So if you put something in the XHTTP directory and you're running on an XHTTP device, it will pick that. However, if you're running on an XXHTTP device and you didn't put anything in that directory, well, they'll get the next closest one, which is the XHTTP. And that's very useful. And you also can do that for layouts. Layouts essentially allow you to arrange components in a logical way. So you say you want the components to flow like this or like that, or become a grid. Then you can define that and build a hierarchy to represent that layout. And the nice thing is that the layout will arrange itself based on available space when you rotate the device, when you run on a tablet or on anything really. They also have a thing called DIPs, which is device-independent pixels. Now, this is very similar in concept points, only instead of it uses the reference device of an MHDPI resolution device as the reference, and they're not accurate. They might be 30% off or so, which might be a problem if you need it to be accurate. But for most purposes where we need to use DIPs, you don't really need accuracy. So it's totally fine in that regard. Last but not least, is something that's called 9-piece or 9-patch. This is one of the nicest things Google incorporated, and actually 9-patch borders, 9-piece borders, is a really, really old graphics pattern that we've been using for years before Android came along. It's not something they invented, although they have a very unique interpretation of that. The thing is that a couple of years ago, I was watching Google I/O, and the speaker was talking about 9-patch borders. Why aren't you all using it? It's so great. And he was very surprised that people aren't using 9-patch borders. Well, when I opened that, and I know 9-patch borders, I know what that is, I knew what to expect. I was presented with a user interface that just sort of had an arrow in it where you're supposed to drag an image in or something. And that's it. No help, nothing. And when you have a user experience like that, well, I understand why people didn't understand what 9-patch changes are. It was sort of user hostile in that regard. But it's a really cool thing. And to understand it, we need to start by thinking about what we usually do when we have backgrounds for components, like, for instance, the button that you see right now. So this button is really a very simple example of how we would build most user interface components that we have. We can just scale it. If we want to put it as a background, we can just scale it to the right side and we're done with it. And most developers look at that and say, okay, great, let's scale. Let's put it as a background image and forget about it. Most designers would be utterly shocked if we do something like that. And the reason is that they would see a lot of distortion in the areas of the corners and to some degree in the sides, the top and bottom and the sides. They'd see the lines getting bigger. They'd see the corners really getting distorted because corners aren't meant to scale. So the solution is actually really, really simple. We cut the image to the 9 pieces that you see in front of you. And we take the corners and sort of pull them apart and put them where we expect them to be in the end. Then we take the sides and we scale the sides or tile the sides so they're not scaled horizontally, because the problem isn't scaling, it's scaling horizontally of the sides. And we do the same thing for the top and bottom section. We scale them horizontally but not vertically. and so, or tile them appropriately. In the case of Google, it's always scaling. And then we scale the center, which isn't a problem at all. We can always scale the center or tile the center. That's it. We now have a larger image, like you see in the bottom image, and it has no distortion. It's very much like the original image, only bigger without the distortion. So that's really, really cool. And I do hope you use some sort of solution like that, either Google's or ours. And one of the cool things that they did here is that they allowed these things to be multi-images. So that's very easy in that regard. So where's the problem, really, if they have these sort of solutions? Well, there's a lot of small things that might not be noticeable in the differences between these platforms. One of the basic things we ran into that sort of represents the problems we ran into when working with Android is there's tablet method. Well, when we run on iOS devices, we just ask, is iPad, and then we get true if it's an iPad, false if it's not. And that's great. We're running on a tablet, we act like a tablet. But when running on an Android device, this sort of didn't work. And the reason is, if you start thinking about all the complex set of Android devices, like the Note and all sorts of devices like that, 5-inch phones and everything, where do you draw the line? Where do you draw the line saying this is a tablet and this isn't? And Google was faced with a complex question and gave back a complex answer of, well, we can't give that answer. You need to decide this DPI, that DPI, this thing, that thing. So there's no real complete is tablet method. Well, we created one by just measuring the size of the screen. If it's 7 inches or larger, it's a tablet. So yes, we sacrifice some devices due to a cutoff point that's arbitrary, but something like that is necessary in order to simplify the lives of us trying to write the actual software to run on this. So that's sort of representative of the issues we ran into when dealing with Google. Apple, on the other hand, is in some regards worse. That's why I said in the opening slide, one Apple device is equivalent to 1,000 Google devices in terms of complexity. So when the iPhone 5 came out, people were practically ripping their hair out. Sorry about repeating all the hair jokes. But it was really painful. And the reason it's so painful is something that most of us aren't really aware of until we actually try to build an iPhone application. When you launch an iPhone application, you notice it launches instantly. Well, you've been lied to. It doesn't. What you really see is a splash screen. iPhone developers essentially take a screenshot of the first screen of the application, and they use it as a splash screen. And what you see is a splash screen loading up, and then suddenly data fills in. A split second afterwards, that's the actual application running. That opening animation that gives you that feeling of launched instantly is really just an image scaling into place, and then it's replaced with the actual running application. Now, this sort of puts some limitations in what you can do in iPhone devices. You can't really have the first screen that's completely customizable, because if you would, then you'd get a really weird effect. So that sort of puts some limitations about customizability and the sorts of things you can do in iOS. But the real pain is with how applications act in that regard. So if I want to change something in the first screen, I need to go and grab a screenshot. Now, when I had the iPhone 3, that wasn't a big deal. One screenshot, great. Then the iPhone 4 came out, 2 screenshots. Then the iPad Retina, 4 screenshots. Then the iPhone 5, 5 screenshots. And technically, iPads can also be run in landscape mode. So 2 more screenshots for Retina and regular iPad in landscape mode. 7 screenshots that we need to take every single time we change something in the home screen in terms of functionality. Naturally, that's a bit painful. It's starting to get painful, at least. And not quite scalable. It's also an issue with size sometimes. For instance, we had a really, really elaborate UI with really complex textured background. And when we grabbed the screenshot for that, it was 3 megabytes for an image, because an iPad Retina resolution is 1536 by 2048. So just grabbing a screenshot of something like that is huge. We had a 20-something megabyte binary just because of screenshots. So now, one of the things we did in Codename 1 was our server actually runs the application 7 times, grabs the screenshot, and generates the screenshots for you. And that's really important because you need a map to grab these screenshots, because you need the right fonts and the right rendering behavior to get everything completely pixel perfect. And it just can't be done on a client machine if it's not a map. So that's really a pain in terms of iOS. There are other things that are really an issue here, but mostly it's the matter of not being able to get everything to be pixel perfect, not being able to get the points per inch to be exactly right. Those are sacrifices we just have to make. Now, a lot of times I hear customers say, "Oh, we want everything to be pixel perfect." Well, they're never pixel perfect on the web. You can't really get them perfect on the web. But you can get something very close, and you can get something similar to that on devices. And that's a sort of compromise you need to make when building mobile applications. So there are several solutions that we can talk about to these problems. And the first obvious solution is the DIPs. Device-independent pixels, the Google solution for it, is really a powerful solution. And we need to pick up on that when we want to build something cross-platform. Obviously, we can't use it to size components because it's not accurate. If we size components based on dips, we'll start running into problems where our fonts aren't correctly aligned and all sorts of things like that, which we do not want to do. But we can use it to padding, for margin, to sort of space things around a bit, where accuracy by the millimeter, well, by the pixel, isn't necessarily as important as it is when dealing with other such devices. We also need to decouple the layout algorithm and do things related to that. So we use a box model, and when we're building web applications and things like that, when we're working with Codename 1, we use layout managers, quite similar to Swing or AWT. And pretty much every solution like that in order to position components in an independent way. Also, we need multi-resolution images, which allow you to get DPI independent images in place. And non-piece borders ideally with multi-resolution images. So how do we do something like that? Well, let's start with a bit of relatively simple code to sort of show you how Google programming is so different from iOS programming. And in both cases, I'm going to use Java because in this particular case, the solution for iOS as well is in Java. Now, this is actual code from Codename 1, and it's open source. Our project is in our open source repository, so you can just go there and see the full code. But this is just sort of a snippet. And as you can see here, this block is really, really simple. We just take the Google's dips to implement our own dips, and we adapt them to be millimeters because we expect dips to be millimeter sizes because, well, we're not Americans. Otherwise, it would have been inches. But we chose to use millimeters because it's a relatively familiar unit, so that most people will just be able to gauge by looking at the ruler on the disk. So that's useful, and designers are very used to working with millimeters as a measuring tool. The equivalent code for iOS shows the stark difference between the platforms. So when I'm dealing with iOS, I literally have physical devices matching things. So I have these large numbers where people measured the exact size of pixel and gave very, very exact size for a specific device. Now, so we literally have code. Okay, it's an iPad. If it's an iPad, then it's the Retina iPad, non-Retina iPad. That's the density. That's it. Is it the phone? Retina phone, non-Retina phone. That's it. Now, you'll notice that this isn't correct, actually, because we have the iPad mini. The iPad mini and the Retina iPad mini have a higher density because they're smaller devices, but there's no way that Apple exposes to distinguish these devices from the regular iPad because Apple thought that's not important. So we can. That's just the way it is. So the applications would be, you would need probably more spacing to sort of work on the iPad mini, and you probably need to test on that device in order to get the correct feeling there. But that's how Apple works, and whether you're doing native or non-native, you won't be able to know that unless you're actually checking device serial numbers and things like that, which you shouldn't be doing generally. So that sort of concludes the first segment. After this short question and answers, I'll have a detour about fragmentation. So I won't be answering questions about fragmentation now. I'll answer them later on in the next Q&A session that we have when we've had time to digest what my opinions on that matter. I'll take a break now, except the presentation, and hopefully I'll have the questions in place. Okay, I'll turn off the video now. Does turning off the video improve sound, Alex? Okay, did anyone hear me through the long talk up until now? Okay, okay, so I think there was an issue with the questions here. I'll disable. Okay, there was a question here from Sammy about Codename 1 and the iPad 4 and animations. Technically, the question is the fluid animations and list crawling specifically. Well, Sammy, I hope you take it up with us in the mailing list for Codename 1. The animations should be as fluid as they are natively because they're technically implemented in OpenGL. I'll talk a bit more about that later on. Specifically, I suggest you try our demos and see if you see fluidity there and to what degree, and we can talk about that there. We use OpenGL technically for all the graphics. So if games are fast on iOS, then they would be fast on Codename 1 as well. Okay, I'll proceed without the video, and hopefully I'll be heard better in the next section about fragmentation. Okay, so let's talk a bit about fragmentation. In the case of fragmentation, there's a big set of people who would claim that multiple resolutions equal more fragmentation. I think that is a complete falsehood. It's more a matter of choice rather than a matter of additional fragmentation. You do need to program differently. There are things we can't really do as easily, like you put in iOS, for instance, the whole 7 screenshot trick. That's problematic to do on Android, obviously. And you can't rely on fonts and images to be exactly right because there's different fonts, different things. That's not necessarily fragmentation. That's variety. And you get variety in the web, and people complain there's fragmentation in the web, but it's doable and it's manageable. And if you code correctly and don't build for IE6 or stuff like that, then the web becomes not as bad. The real fragmentation in Android is more niche. It's not related to that. It's related to mostly to bugs. So, for instance, we ran into issues with cameras where the second shot you take in a camera in a specific device would fail for various reasons. And it will just crash the device regardless, or at least the application. And there are workarounds for that, but then you have to start coding all sorts of workarounds. Now, Google fixed some of these things in the operating system. However, when they fixed them in the operating system, they ran into the issue of the vendors not actually shipping newer versions of the operating system. And when that started happening, Google shifted a lot of their fixes and new features into the Android Market tool, which is proprietary. So effectively, Android is less open source now than it was when it debuted. And the Android Market is proprietary to Google. So you end up having something that Amazon doesn't have access to. And other vendors that don't have official Google devices don't have access to. And you increase fragmentation. You essentially create a different type of fragmentation. Now, and Samsung as well is trying to co-opt some of these things, and fragmentation is slightly increasing. So in some regards, fragmentation is improving because Google is moving a lot of the functionality into the market. On the other hand, it's getting worse because Google is moving a lot of the functionality into the market. So I'm saying there is fragmentation, but it's more of the operating system version fragmentation, device bug fragmentation, things like that. Not so much related to resolutions. And it's not as big a deal for some cases than it is for others, but you do need to test a lot and you do need to be responsive, and Google does offer lots of great tools for doing that. So to pardon fragmentation. Let's talk about scene graph and immediate mode a bit. And in this section, I'll talk about how devices differ in how they render graphics. Now, I use the term immediate mode because there isn't really any other term to do that. And in terms of the opposite of scene graph isn't really, well, there's really no name for that. But it should be familiar to all of us who do Java, and most of us who do pretty much anything, because that was the way Windows used to work back in the day. It doesn't anymore with the changes of Windows 8 and XAML, but it used to work that way. And most operating systems and most platforms used to work in this particular way. In recent years, there's more and more adoption to the idea of using scene graph. Apple, mostly Flash, led the way there actually in a great way. SVG is also a scene graph, obviously. iOS is a scene graph internally, although it does provide an immediate mode API. Since iOS 4, its performance sort of became unusable. So it's no longer an option for most of us. Immediate mode is sort of like Paint. So when we're working with immediate mode, we expect, if you're used to Java, you get the sort of paint and get the graphics as an argument whenever you need to draw the screen. And you can also invoke repaint in order to trigger an actual paint. So in that particular case, you can essentially do draw the screen completely within that paint method and don't really need to think all that much about it. You just get the graphics, you get to draw things, and it sort of appears on the screen. You always draw everything. You don't really need to spend any time constructing anything. It's really, really simple, and not so much, it's just drawing. On the other hand, the scene graph is a really complex idea. In scene graph, we generally need to create a graph structure to render things. So if, for instance, in a paint environment, we get a graphics object and just invoke graphics.draw rectangle, and it would draw it on the screen in the given coordinates. In the scene graph, we'd essentially construct a tree, and into that tree, we'll add that rectangle object. And that would sort of be drawn in the screen. We won't get a repaint. We won't be able to determine when the screen is painted or how. It will just happen at its own accord. Now, if we want to rotate that rectangle, we can just add a rotate transform node above that rectangle, and the rectangle will be rotated. Now, that's pretty elaborate and complex, and when usually we explain scene graph to people, they say, well, that's really complex. Why would someone want to do that? Well, there's several things. First of all, it can be hardware accelerated in potential. Because you don't do the whole rendering yourself, you don't draw on your own accord, the system can actually optimize the rendering process very well. And that way, the graphics can be very smooth and potential. That animations are also a great source for optimization here, but they're also a great source for difficulty. So if, for instance, I want to take that rectangle and I want to animate its rotation, well, then I have a tree with a rectangle without a transform, and then I want to convert that tree, to mutate that tree into a tree that has a transform that rotates the rectangle. Well, that whole process of mutating that tree is a really complex API, and it's not. And the value here is that when we define that particular API, we can define motions between areas that create a sort of rotation that is very smooth and very attractive. And that's one of the things that pulled people into the scene graph mentality. It's the ability to do these things relatively seamlessly. And that's really, really cool. And because it's a very uniform and very constrained API, you usually get a really good effect overall. So which one's better? Well, they're both good, essentially. Each one has their own advantages and disadvantages. Scene graph is more, well, the graphics buffs usually prefer scene graph. Immediate mode is considered to be more gaming fashionable generally, although even there's some changes. But generally, it's easier to prototype things faster in immediate mode. Scene graph is more elaborate in some regards. But generally, this is to some degree an academic discussion, because when we're doing the low-level stuff, the graphics, there's a difference. But when we reach the higher level, the components, the widgets, the tables, the buttons, they're all scene graph, because when we add a button into UI, then we have a tree that represents the button, and a container that contains it, and the window that contains it, and everything. So we always have a scene graph. The question is, when does the scene graph come into being? It can come into being during the stage where we create the graphics themselves, and then the button needs to map into a scene graph, or it can be a scene graph in the stage where components exist. So when we animate the components, we'll always get the benefits of a scene graph, regardless of whether a scene graph is used underneath. However, when we do graphics without a scene graph, we need to know what we're doing to some degree in order to get a nice looking effect. And now, why is this important when I'm talking about portability? Well, as I said, when we're looking at iOS, iOS has a scene graph API. Yes, it has an immediate mode API, but it's ridiculously slow. So the only option is to use the scene graph API, it would seem. The problem is that if I have a scene graph and they have a scene graph, and we try to map two scene graphs one to the other, this is a problem because they're incompatible. There's no standard. If I want to use an immediate mode API, it's relatively simple to map in a cross-platform way. Usually you have a draw image method, usually you have draw string method. These are really simple and standard things that exist in practically every platform. But when you want to map a scene graph API, because of the sheer complexity of that API, it's just impossible to sort of abstract it in a portable way. So there are solutions like that. JavaFX and effectively Flash are essentially scene graph APIs. And the thing is that they work on iOS to some degree or other. And the way that they did that was implemented on top of OpenGL rather than implemented on top of the scene graph that's available in iOS, because it's just impossible to map to a scene graph. And that seems to work okay. The problem is that things like fonts usually don't work in OpenGL or in all gaming APIs. Now, the thing is that gaming APIs are almost always instant. They almost always use an instant access to the GPU and instant access to the screen. Not necessarily immediate mode because it's used in different contexts when we're talking about OpenGL, so I don't want to confuse you if you're familiar with that. But it's sort of an API that allows you direct access to the graphics to draw things instantly. And on iOS, that's pretty easy. We can just do something like drawing a texture and essentially drawing the string onto a texture and just work with that. And there's a bit of OpenGL code here. I won't torture you too much with going over what we did with the OpenGL code in order to draw a string in OpenGL. But the thing is that this essentially works for iOS with OpenGL, and that's how we did it there in order to give relatively fast graphics there. The problem is that platforms like Windows Phone don't really provide such a solution. So when we're running on Windows Phone, we're essentially stuck because Windows Phone only has a scene graph mode where it allows you to draw text. It doesn't have any sort of mode where you can both draw text properly and the immediate mode. So it has direct text really, where you can draw graphics fast. But in that mode, you can't really draw a string. And that is, or even place a text edit component or anything like that. You can't do that. And that's a huge problem with Windows Phone. And the only workaround we had was to actually map the scene graph in Windows Phone directly to immediate mode. This has huge performance implications and issues. We worked around a lot of them, but it's a real pain. And currently Windows Phone is one of the worst platforms to work with for us, at least, in terms of portability. It's a really difficult platform in that regard because of the scene graph concept that's prevalent there and no alternative to working around it. So we can stop again for another short question and answers. I hope I can address some of these additional questions. I'm seeing here a question that there's still a lot of distortions in the audio. I hope that's just for one particular user. I hope that's not a global problem. Well, my answer to the previous question about the Codename 1 performance is you should talk to us on the Codename 1 forum and check some of our demos out and see if you see the same issues there. We're obviously always trying to improve performance, but I think our performance is really good in that regard. And I'm going to talk in the next section about performance quite a lot and how we measure performance and how we work in terms of performance. Not as much in terms of graphics performance, mostly because my OpenGL sucks. Sorry, I'm not the greatest OpenGL hacker there is. But what we do essentially in terms of performance is just blit. And one of the things, actually, I think I forgot in the slides where I was talking right now is the mention of vector graphics. When we're talking performance, vector graphics are very expensive in terms of performance, but images, raster images, move really, really fast, and devices don't have support for vector graphics built in. They have it in WebKit, but not generally within the solution, the native solution. So you see a PNG support, an raster image support, because that's just really easy to upload to the GPU and just render instantly. But with vector graphics, there's more CPU involved. Now, the main problem isn't so much the CPU performance, but rather the fact that it takes from the battery life. So they don't have any native built-in support for SVG, which would seem like the ideal solution for high DPI devices. Now, what we do is pretty much just shove textures around really, really fast. And that's fast. That's really fast. And games do that all the time. And because we're sort of sitting on that niche where games provide performance benefits, and we use the same performance footprint of the game, we can give that same performance to an application. So our performance should be equivalent to the performance of a game, which should be pretty good, regardless of the platform. Ibanesu Bogdan, I don't understand your question quite correctly. I'm not sure I understand your question. I'll address it next time if it's still relevant. So let's talk a bit about performance, and I'll try to focus more about performance also in terms of graphics and how to work with it. So I hope everyone listening is familiar with the term JIT, just-in-time compiler. Essentially, when it runs, when you run an application, a typical Java application or JavaScript application, you get to a position where the bytecode is interpreted and essentially translated to native code in runtime. Now, this seems like a really, really complex thing, and people often, those who haven't written a compiler, think of it as sort of a black magic sort of thing. It isn't. It's relatively simple. It's relatively easy to write a compiler and relatively easy to write a JIT. The complexity isn't in writing a JIT or a compiler. They're mostly static code that just translates a representation to another representation. Relatively simple. The thing that's interesting about a JIT is the optimizer, and that's the complex portion of a JIT, and that's the core, the meat of it, really, the hard part. So, but the thing is, device JITs have a very complex optimization thing. Device JITs aren't optimized for speed. So, a while back, I think Xamarin produced a benchmark where their C# JIT was much faster than Dalvik, the virtual machine from Google. And Sun Oracle also produced a benchmark where their Java implementation was much faster than the Dalvik implementation from Google. The thing is that this is sort of a red herring thing, because a device JIT is optimized for battery life, it's optimized for low memory, which is hugely important, more important than speed, and it's optimized for security. These three things are far more important for a device developer than the performance, the raw performance. And when we take these things into consideration, Dalvik is pretty good. Our old JIT at Sun Microsystems that was meant for devices actually had this really nifty ability where it could garbage collect bytecode from memory And that was really, really cool, because if the JIT was over anxious and collected and sort of over compiled things, then you'd have a lot of bytecode, a lot of assembly code in memory, and not enough memory. So the choice suddenly becomes: do I run fast and crash, or do I run slow and still run? And the JIT made the wise choice of being able to collect compiled code. This is something that doesn't exist in the JIT for desktop. It was purely a mobile thing. And that's important because sometimes a mobile device can have 2 megabytes of RAM. I'm talking about old feature phones, actually probably more in that particular JIT. But you'd really, really want to conserve memory as much as you possibly can. So the JITs are really, really cool, but Apple doesn't allow them. And usually when we think about, oh, Apple doesn't allow, we think, oh, those guys at Cupertino are also trying to control everything. But the thing is, it makes a lot of sense. JITs in a mobile device would be would be a huge problem in an iOS device, because you could essentially have self-modifying code and inject malicious code directly into the device. So Apple blocks it both in the operating system level, and it blocks it in the higher level, sort of in terms of the license. So they won't let you have a JIT on the device. So the only solution is to compile ahead of time, or as pretty much every other language calls it, to compile code, to actually get a native application that doesn't modify itself. Now, but Java, or more correctly, the Java API wasn't designed for that. We have reflection, we have class loading, we have bytecode manipulation, all sorts of things like that. They don't really fit well with JITting, without JITting, really. So why not just throw away Java altogether? Why just, say, okay, let's do something else? Well, the reason is that Java is the native platform for Android. So we have that advantage of having a solid home base and being able to go from it to iOS, to other platforms as well. And that's a really, really good starting point that, for instance, C# doesn't have, because in the case of C#, for instance, the home base is Windows Phone, so that's a pretty weak home base. So that's a Windows Phone Microsoft Slam. Yeah. Anyway, so, and the thing is that Java has a very good redeeming quality of having bytecode that's really easy to compile. And that's really, really important. And the reason it's important is because we can get very optimal performance from bytecode translation. The thing is that the API is a problem. And the API includes a lot of clutter. For instance, this is from running a Java 1.6 Hello World application that does nothing except print Hello World. You get 600 classes loaded just to show that. Now, by the way, loaded, not initialized. These are very important distinctions, but still, there's a cost. So when we're talking about AOT compilation, initially when we started coding one, we said, let's implement our own AOT compiler. But after a while, we saw Xmlvm, and Xmlvm was actually immature when we started working. But as we progressed, we saw it mature into a decent solution. So we picked that, and Xmlvm turned out to be a pretty solid choice in most regards, and a really good option. What Xmlvm does, it's essentially, it's sort of an XSLT converter. It converts Java bytecode to C code, which we can then compile using Xcode, using the standard iOS toolset, and build a native application as a result. And that's pretty cool because we can use Macs and standard Apple tools. And so if Apple makes a change to Xcode, which happens quite often, we can still work with that. There's also J2 Objective-C, which I'm mentioning here mostly for completeness. Not because it's not a great tool. It is a great tool. but it's not the JVM. J2 Objective-C allows you to take Java sources and translate them to Objective-C sources, and you can then compile them. Now, the thing is, it's not meant to be used as a JVM. It's meant to be used as a sort of tool to allow libraries to be compiled, to be shared between Java and iPhone developers. And it's really good for that. And it's the only tool of these four that allows building libraries properly. And these libraries are a bit odd because you need to be aware of how memory is managed in Objective-C. It doesn't have a garbage collector or anything like that. So you need to be aware of that and need to build things for that. And we'll talk about that a bit more soon enough. But you need to be able to build it in that way. Now, the tool itself is pretty powerful. It's very similar to GWT if you're familiar with that. RoboVM is the latest arrival to the scene, and it's an LLVM front-end, which is really a compiler. It compiles Java code directly, Java bytecode directly to native ARM code for iOS, and it's a really cool solution in that regard. It's still immature to our tastes, but we're keeping a very close eye on it, and I think it's moving along very nicely, and we might migrate to it at some point or other, depending on how it matures as it moves forward. And Avian is one of the more unique options here. It's an actual JVM with an interpreter, with a JIT, and with an AOT option that can run on iOS and can run on other platforms as well. But it's a very ambitious solution. It's designed for more general purpose. So I'll mostly focus on RoboVM and Xmlvm, both of which are really good solutions here. They're both very similar in performance when checked on the devices. The difference is RoboVM is a bit faster, not by much. Both exceed Objective-C in terms of performance for things like method invocation. Now, Objective-C doesn't have methods, it has messages, which is sort of me cheating and saying, okay, we're faster in method invocations because we have methods. If you'd compare it to function calls in C, then it would be slower. But Objective-C itself as a language isn't very fast. And this is something people often, when I say this, often have a knee-jerk reaction of me being full of it. Well, it isn't. It isn't very fast as a language. But what you see as the speed of iOS is a set of really, really great optimizations. It's the core animation graphics layer, which is really, really, really fast. And it's really well integrated into their whole component environment. But the language itself, it has some elements of C which are fast, but things like message dispatching, memory management, etc., aren't very fast, although they are deterministic, which I'll talk about in an upcoming slide. When we see performance issues, usually they relate to the application or the API layer when using something specific in the API or something that isn't optimized for a particular platform, particular use. Not as much in terms of the Java code. And the reason that we don't really see that is that the Java code isn't really all that complex. It's just translated to C. And usually that's really, really simple, and the compiler knows how to optimize it really, really, really well. If you do actually run into something that's really slow in a Wara solution, all decent Wara solutions allow you to write some native code, so you can always do some of that. Now, the section that does the graphics, which is the interesting portion here, that's native. That's entirely C Objective-C code that we wrote, hand wrote. And that's the heavy lifting. That's when you know there's a rule of 1090 or 2080, where most of the performance and time is spent in 10% of the code, 20% of the code, depending on whose version of this rule you listen to. Well, graphics is usually the bottleneck when dealing with this. And graphics is actually why HTML5 has performance issues, because it constantly reflows things. In our case, the graphics are implemented entirely in native. So if there are performance in that layer, then we can improve the native portion. And so the performance of the JVM isn't as critical to general application performance. So, but one of the contention points here, and one contention that recently in the Slashdot article, an article of mine that got Slashdotted, a lot of people took pains to argue with me over, is that GC is a problem. That GC is supposedly slow, or not so much slow as non-deterministic. That GCs essentially create peaks in performance where you see major delay or skipping in the UI. Well, and they often compare that to ARC. Now, if you've talked with iOS developers, and I'm assuming most listeners aren't iOS developers, then you might have heard about ARC or iPhone's GC. Well, iOS doesn't have a GC. There was an experimental thing that they sort of killed and deprecated. And they have a thing called ARC, which is automatic reference counting. Now, if you come from a history of C++ or stuff like that, and reference counting might be familiar to you. In reference counting, essentially, when we allocate an object, we have an int counter on that object. And every object that holds a reference to that object increments that entry. In Objective-C terms, it's retain. You invoke retain, and that sort of increments the number on that particular object. When you are finished with the object, you call release, and that decrements, that reduces the number. When that number reaches 0, that object is automatically deleted, which is pretty simple and pretty convenient. You just have to remember to call retain and then call release every time, which is tedious. So Apple added this thing called Odo Release Pool. Now, Odo Release Pool essentially allows you to pool objects together. So an object that is auto-released is added to the currently global Odo Release Pool. And when you call release, that Odo Release Pool is automatically released. It releases all the elements within. And that's really convenient because you don't have to individually call when you allocate lots of objects. You don't have to call release on every one of them or retain on every one of them. They just sort of automatically get collected. And ARC automates that particular thing. ARC sort of eliminates the auto-release pool thing and allows you to automatically retain and release components, objects. So now the thing is that the auto-release pool is very, the thing is, sorry, about ARC is that ARC is really, it simplifies the easiest portion about reference counting. But when you have things like cyclic references or things of that sort of memory leaks that come together with reference counting and the issues related to reference counting, that last 5 or 2% of the problems that are the hardest problems by far, those aren't simplified. And ARC doesn't do anything to solve them. So it's not really a garbage collector. A garbage collector solves the whole problem. And ARC solves the easiest 90% of the problem and sort of leaves you to deal with the mess of the hardest portion of the problem. So there's no alternative for GC, not really. The thing is, GCs have pretty good performance when you code to the GC. And this is most of what I'm going to talk about in this slide, how to code to a GC. And most developers who haven't written native code might not have a clear picture of what it means to code to a GC. Well, in Java, when we have a regular object and we allocate it, then it gets released. This is pretty easy. This is easy for the GC. It's easy for us. We can allocate and throw away objects. There's generational GC and all sorts of things like that, but that's mostly applicable to the server, not so much for mobile where we have relatively small heaps. So allocation and deallocation with the GC is relatively simple and relatively fast. The problem is with finalization. So Java allows you to essentially have a finalize method that allows you to clean native resources. And that's a really powerful tool. Now, one of the important things about this is that when an object, for instance, an image object, it might be a very small object. So when the garbage collector tries to collect it, it might inspect it and it looks like a really small object that doesn't hold much memory. But in reality, because it holds lots of native objects in memory, it could be a very, very heavy object, despite looking relatively small. So garbage collectors can't really discriminate either. And it's a really complex part of garbage collection authoring. But I digress a bit. The finalize method essentially allows you to delete that native memory that's maintained. The problem is that we don't really have a destructor in Java, except for finalization. And finalization happens during GC. So the way the GC works is the GC runs over the heap, finds the objects that are ready for deletion, and sort of marks them. Then when it actually tries to delete the object, it runs over the object and says, okay, this object has a finalizer, I can't delete it now. It adds it to the finalization queue, and the deletion of the object is sort of postponed to the next cycle of the GC. So essentially, if you have an object that has a native element associated with it, it won't get garbage collected when you're out of memory. So if you're allocating images left and right, and then garbage collection happens, garbage collection won't deliver that much because it will still be waiting for the native finalization. And you might run into a problem with important to be very dynamic in that regard. And if you're at a point in your application where you need to be fast, so for instance, you're building a game and you need rendering to be really, really fast because you're in the middle of a level, don't allocate images, don't allocate audio, don't allocate anything. Allocate them before starting the level. And then all the objects that have native data associated with them will remain in memory during the level, which, yes, it will cost you, but you need to have that memory available anyway. And then release them only when you're finished, when you have time, when you're willing to have a GC cycle run. So you need to manage this GC in that regard. So if we have native resources associated, we'll essentially wait at least 2 GC cycles until something is actually released, and we can actually fully reclaim that memory. And that memory might be really, really problematic, because in the case of an image, for instance, in Codename 1, we sometimes might have double the memory associated with a particular image, because it might be allocated in native memory and on the texture memory for the GPU, which is a volatile memory. And I can get more into that, but generally, a GPU memory is often duplicate in some regards. So we might be very wasteful when dealing with GPU memory. And that's mostly a matter of performance. And the reason it's that way is because pulling data out of the GPU is really, really slow, but pushing it in is, you don't want to do it too frequently. So when we have a texture in the GPU, we don't want to touch that unless we don't have a choice. We might also still keep it in Java memory if we need the byte data as well. So this can become very, very expensive, and you could be paying for a lot of memory, even for a relatively small object. So we need to reduce allocations in that and in native components, native objects. Now, how do you know when you're allocating an object, whether you're allocating a native object or a non-native object? Well, that's usually pretty easy, because images will always have a mapping to a native object somewhere. And so with audio elements, and some UI widgets might also have that, although in our case they won't, but in cases of an API like AWT or SWT, they will. So you just need to have some awareness of what the platform is doing if you're trying to be very performance sensitive. For most developers, being at that level, unless you're building a game, doesn't really matter. This is something we usually need to know. And although you should also be aware of that when you're working with images frequently, just don't constantly create and discard images if you can avoid that. But I'm guessing that's mostly obvious. Don't overdo. So there are several strategies that we're using in order to optimize this whole thing. And the first is to use weak and soft references to cache. And if you're not familiar with weak or soft references, weak and soft references essentially allow you to keep a pointer to an object, but still allow the garbage collector to delete it. And that's a really, really powerful tool, because the garbage collector can essentially delete an object while we still have a pointer to it. But if it doesn't delete it, we might be able to recover that object and might be able to use it. So for instance, with encoded images, we have this really, really cool thing where we can actually keep a reference to the native image, but for reuse. So we don't have to constantly create and delete it, and actually keep it in memory, but don't pay as much for it. So an encoded image is one of the tricks we do, where we store the image as a PNG in memory, which is the bare minimum. That the actual compressed image is stored in memory. And when we need access to the image, we decode the image on the fly. Now, the thing is that that's pretty expensive. We don't want to do it every time, but it's really useful. So we can keep a reference to the decoded image as a weak reference. And at that point, we can effectively draw that weak reference if it's still in cache. Now, this might be very expensive if the image is currently shown on the screen. So we have an optimization to convert the weak reference to a hard reference as we're running on the screen. And that's also very useful. So I hope you have questions, because I'm nearing the summary and the end, so please post as much questions as you want. So the summary is generally, when you're trying to build graphics and a cross-platform experience, the UI fidelity is one of the hardest issues when you're dealing in cross-platform, because you can't really, when you're targeting so many devices, just Android alone is huge. And you won't be able to get the same UI fidelity always, but you can do that, and it's not, and it's very possible, at least at web levels, if not better. There are lots of strategies to dealing with the issues between devices. We talked about it. And the performance issue, that's hugely important, and it's usually an issue of applications and porting layers, more than it is an issue of the virtual machine itself. At least in all of our benchmarks, that has proven to be the case. And I hope you accept some of my claims about device fragmentation. I didn't talk about a lot of things because I am running out of time, and pretty much timed it to run out of time. So, but there's so many issues related to threads, I/O, native access, and device fragmentation, and device features that we can talk about. Especially threads is a session in its own right in terms of the issues that we run into when developing cross-device applications. So thank you all for being here, and I hope, and I'll try to answer as many of your questions now as I possibly can. Please feel free to post them in the question and answer section. Well, PhoneGap difference question in the chat actually is difference between PhoneGap and Codename 1. Well, PhoneGap and Codename 1 are actually very different. PhoneGap is an HTML5 solution, where codename 1 is a Java solution. And essentially, PhoneGap is something that was written in a hackathon where codename 1 took us roughly 7 years of hard work. So there is a bit of a difference there. PhoneGap generally is just a web view that packages HTML and JavaScript directly into the application. Now, I'm not to diss on PhoneGap and the hard work that they did, but the real people who did the work there are the guys who wrote WebKit. And if you like HTML, then PhoneGap, great, works for you. Obviously, HTML and JavaScript weren't designed to work that way. They were designed to work with a server. And that is a problem. And I suggest you also check out, I had a post about why the mobile web is slow, which talks a bit about why HTML5 is slow and why it will always be slow because of essentially constant reflows. Codename 1 is really proper Java in that regard. It gives you threads, we draw everything, we give you access to native, and we have the build server system, which is very different to what PhoneGap does actually. Let's try going through it in order. Well, there was a question here about Xmlvm and the primitive to Xmlvm. Well, I hope I answered that particular question about Xmlvm in my slides about that. I think it's currently the best solution there is. If there is a better solution, if RoboVM proves itself to be better, because codename 1 is an abstraction, we're not the VM. We use a VM. Although we might implement one of our own in the future if we choose to, but because both of these solutions are really good, we don't feel the need to reinvent the wheel. We'd rather contribute to those solutions instead. And so that's what we're doing. Essentially, we have our own fork of Xmlvm, mostly because of logistics. I've talked with the authors of both actually in the latest Java 1. I've talked with both with Nicholas and Arno, both really wonderful, very, very bright people. And both of these are great solutions. And also JP Objective-C, although it's targeting something different, and also Avian, they're all good solutions. They're low level. We're trying to sort of address the higher level problem at hand, which is a very different problem, in my opinion. Ibn, I still, yeah, okay. So never mind. Well, about rich text widget in codename 1, I think, well, there's an answer that someone developed it already, yeah. There are several implementations of that, both from Steve Hanna and other sources as well. Anastasia asked, can I develop for iOS, Android, and Windows Phone codename 1 only from Eclipse? Eclipse and NetBeans and IDEA hopefully in the near future. Yes, you can. Very easy. Well, as I said earlier with HTML5, and you can also read my blog post about HTML5, why the mobile web is slow. One additional problem with HTML5 is the support for DPI. Normally, HTML was designed for working in a case where you have a server, and the server could actually give images in the DPI independent mode. So if you have, if you detect a device that's high DPI, low DPI, you can return the right image for a specific device. But in the case of a mobile application that's running on the device, you don't have the server, so you have to write all the logic in JavaScript. Now, a lot of people, when I say that, say, okay, there's responsive web that works really well for something, but it's really difficult. And when you start dealing with responsive web and DPI and 9-piece borders and stuff like that, then there's not that much standardization. and there won't be, because PhoneGap isn't a standard. The standard is HTML that's designed for the web and not for embedding. And so it's not clear whether, they like to put the feather in their cap of being a standard, but that's like me saying that Java is a standard, that's why Codename 1 is a standard. That's not true. And the same isn't true for that case as well. So that's about HTML5. Obviously, I'm not a fan, but I'm not exactly objective, as everyone I'm sure realizes. What are the advantages of Codename 1 compared to other frameworks in the market? Well, I don't think there are other frameworks in the market. Actually, when you go to the Aurora page in Wikipedia, you see like 200 cross-platform tools, but you can filter most of them out because they're all HTML5 solutions. And when you check out the remaining solutions, there's solutions like Xamarin, which isn't really a write once run anywhere solution. You need to port it to every platform, and that's a lot of the rest, where you need to actually port to every single platform. And then you remain with a relatively small group. Out of that group, a lot of them have things like a lowest common denominator approach, where they sort of like Accelerator, where they work with native widgets and they place these widgets and they sort of created abstractions for the various widgets. The problem with that approach is that it's write once crash everywhere. And the reason is that iOS is so radically different from Android that the API has a really strong bias. And it's really, 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 now I want to say really hard, I'll say it's impossible to do this properly. And you end up paying for that. And I talk to lots of people who like companies like Xamarin that are doing really wonderful things. I don't want to go badmouth all competitors. Xamarin's doing a great job. Accelerator, I've yet to run into a guy who likes them. If you do, please drop me a line. I'd love to talk to you about it, because I've been searching really hard for someone who actually likes Xamarin. Accelerator. Xamarin's good. But Xamarin's obviously not a Aurora solution. The Aurora solutions, you don't see all that much, and those that you do see are generally limited for graphics or gaming. And no one actually does desktop, really mobile application development in Java, in mobile, and Aurora. So I think we're on our own in that regard. I would not use Codename 1 for developing Windows Phone apps right now, because our solution isn't as mature on Windows Phone, but we are working on that, and it's a high priority to get it properly working in the near future. We do not plan to split Codename 1 to be more lightweight. There is Luet that is still relevant for J2ME. If you want something lighter weight, I suggest going with Luet. It's sort of a race to the bottom is never a good idea. And when you're a startup and you have limited resources, supporting devices like, sorry, I didn't read out the question, that's split Codename 1 to support platforms like J2ME better. Even when we wrote Luet at the time, we always targeted phones from the past 3 years. And we still hold roughly by that mantra, and actually go further. We go 4 or 5 years back for most cases. So we probably won't support older devices, older J2ME devices in the future. I think that's all the questions. Am I correct, Alex?
Thank you, Shai. Thank you for taking us through the material. Judging by the number of questions and the attendees, I think the session was highly regarded. Thank you for accepting our invitation to this webinar. I highly appreciate that. To all of the attendees, thank you very much for being with us. As you log out, we would appreciate if you filled out the short survey that will be displayed to you to give us some feedback about the session and ideas for the future sessions. We plan another LTS webinar in November. If you want to follow us, please take a look at www.luxoft.com/LTS. If you would like to learn more about Luxoft, please visit our career site at luxoft.com/careers. Thank you very much for attending. Shai, thank you once again for conducting the session. Thank you to all of the technical team who was looking after this webinar and organizing it. And this concludes the session. Thank you.